Welcome to Tungal Online Classes. In previous video, we have discussed the concept of Pascal's law and the applications of a Pascal's law. So today, we are going to discuss about energy possessed by the liquid, right? So if the liquid is in motion, it possesses three types of energy. First one is kinetic energy, second one is a potential energy, and the third one is a pressure energy. So in that first one is kinetic energy. Okay, see here, the kinetic energy means the energy possessed by the liquid due to its motion. So that is known as the kinetic energy. Okay, see here, the energy possessed by the liquid due to its motion, so that is known as the kinetic energy of the liquid, right? The energy possessed by the liquid due to its motion. So already we know that expression to calculate the kinetic energy is, that is kinetic energy equal to 1 by 2 m into v square. Here K indicates that kinetic energy, m indicates the mass of a liquid, v indicates that the speed of that liquid. So this is the kinetic energy formula. So next one, kinetic energy per unit volume. Kinetic energy per unit volume. Per unit volume means we are dividing both sides by volume. So then kinetic energy per unit volume, that is equal to 1 by 2 mass into speed square divided by V, right? V indicates that is volume. Here capital V indicates that this is the volume. So already we know that the definition of density, so density is equal to mass per unit volume. Density is equal to mass per unit volume. So here we are replaced m by v as a density. So this is 1 by 2 rho into v square. So this is the kinetic energy per unit volume. Okay, so here the kinetic energy means the energy possessed by the liquid due to its motion, and its expression is kinetic energy equal to 1 by 2 m into v square. Then the kinetic energy per unit volume, that is equal to 1 by 2 m into v square divided by volume. From the definition of a density, density is equal to mass per unit volume. Here mass per unit volume, it is replaced by the density, that is 1 by 2 rho into v square. So this expression is the kinetic energy per unit volume. Kinetic energy per unit volume. The second one is the potential energy. Potential energy means the energy possessed by the liquid by virtue of its position. So that is known as the potential energy of the liquid. Okay, see here, the energy possessed by the liquid energy possessed by the liquid by virtue of which its position, so that is known as the potential energy of the liquid. So already we know that the expression to calculate the potential energy, that is mgh, right? So the expression to calculate the potential energy is, that is mgh. So then potential energy per unit volume, that is equal to mgh whole divided by volume. So already we know that mass per unit volume is nothing but the density. So then expression to calculate the potential energy per unit volume is, that is rho gh, So this is the kinetic energy, and the kinetic energy per unit volume expression, that is 1 by 2 rho into v square, and this is a potential energy, and this is a potential energy per unit volume expression, that is rho gh. The next one is pressure energy. Then what do you mean by the pressure energy? So pressure energy means the energy possessed by the liquid by virtue of its pressure. So that is known as the pressure energy. Yes, here the energy possessed by the liquid by virtue of by virtue of its pressure, by virtue of its pressure, so that is known as the pressure energy. Okay, the energy possessed by the liquid by virtue of its pressure, that is known as the pressure energy. So next one we are going to find out the expression to calculate the pressure energy. For this one we are consider a vessel, at one side we are fitted with a frictionless piston. So consider this is a vessel, at one side we are fitted a frictionless piston, and this vessel is filled with some liquid. This vessel is filled with some liquid of density, so that is rho, and the area of a cross section of the vessel is, that is A. So in this case we want to shift the position of this piston from P to Q. Here we want to shift the position of a piston from P to Q. For that one we have to do some amount of work done. So for that reason we are applying some amount of force. We are applying some amount of force on the piston in this direction. So due to that force, the position of the piston changes from P to Q. The position of the piston changes from P to Q. It covers some distance, so that is X. It covers some distance, that is X. Okay, see here, in this case, if you want to shift the position of the piston from P to Q, we have to do some amount of work done. For that reason, we are applying some amount of force on this piston. That piston move from P to Q and it covers some distance, that is X. So then, work done is equal to, already we know that the work done means that is force into displacement, force into displacement, force into displacement. Here force value is, that is F, and displacement is Ex. From the definition of a pressure, pressure is equal to force per unit area, then force equal to pressure into area. So substitute the F value here, pressure into area into X. This is the work done. So in this case, area into displacement is nothing but the volume. Okay, so here volume it can be written as area into height. So here area into displacement of the liquid, so that is known as the volume. Then we will replace A into X by V. So then work done, that is equal to P into V. The work done is equal to P into V. So in this case, this work done is stored in the form of pressure energy, that is pressure energy. So pressure energy, that is equal to P into V. So then pressure energy per unit volume, pressure energy per unit volume, that is equal to pressure energy is, that is P into V divided by per unit volume is volume get cancelled. The pressure energy per unit volume value is, that is P, right? So these are the energy possessed by the liquid. The first one is kinetic energy, potential energy, and the last one is the pressure energy. The next one is Bernoullis Principle, right? So it is very important. So what is the statement of this Bernoullis Principle? It is a sum of kinetic energy, potential energy, and pressure energy per unit volume is always constant, for an ideal fluid having streamline flow. So this is the statement of a Bernoullis Principle. So what is the statement here? It is a sum of kinetic energy, potential energy, pressure energy per unit volume is always constant for an ideal fluid having streamline flow. Okay, see here, it is sum of kinetic energy, potential energy, and pressure energy per unit volume is always constant for an ideal fluid having streamline flow. So according to this statement, the sum of kinetic energy, potential energy, pressure energy per unit volume is always constant for an ideal fluid having streamline flow. Because here there is kinetic energy, potential energy plus pressure energy per unit volume that is equal to constant. So already we know that the kinetic energy per unit volume expression is, that is 1 by 2 rho into v square plus potential energy, that is rho gh, plus pressure energy per unit volume, that is P, that is equal to constant. P plus rho gh plus 1 by 2 rho v square, that is equal to constant. The next one, we are going to prove this principle. For this one, we are going to consider a bend shaped tube of having different area of a cross section. Consider this is a bend shaped tube. So this is the first phase, that is A, and this is the second phase, that is B. The area of a cross section of the first phase is, that is A1. The area of a cross section of a second phase is, that is A2, and this is our reference level or horizontal surface. Here this second phase at a height h2 from the horizontal surface, and the first phase it is at a height h1 from the horizontal surface. So in this case, if the liquid is enter at the point A and it exit at the point B, right? So here V1 be the speed of a liquid or the velocity of a liquid is enter at a point A, and V2 is the speed of a liquid, it is exit from the point B, right? So here the pressure P1, here the pressure at this point is P1 and the pressure at this point is, that is P2, right? Okay, see here, if a liquid is flowing from point A with some velocity, that is V1, and is exit at point B with a velocity, that is V2. Okay, in this case we are consider in a small time interval del of t. In a small time interval del of t, the fluid it covers some distance, right? So fluid it covers some distance, right? So at this point is also at the time interval of small time interval del of t, that liquid it covers a small distance, right? So for example, so this is a point P to Q and this is R to S. In a small time interval, that fluid covers from point P to point R, and here in the same time interval that fluid covers distance from X to Y. So then first we are going to find out the work done by the pressure. Work done by the pressure. Work done by the pressure at point A. At point A. So that is equal to, at this point already we know that the work done, here we will consider that is a W1, that is equal to force into displacement. Force into displacement. Here the force is, that is F or F1 into displacement, it covers a small distance or small displacement, that is dx. This is dx. So from the definition of a pressure, so pressure is equal to force per unit area, then force is equal to pressure into area. Okay, see here, then F1 is equal to, that is P1 pressure into area into small displacement, that is dx, right? See here, the area into small displacement dx, it is considered as the volume. Then W1 is equal to P1 A into del of X. So this is P1 into del of V, right? So this is the work done by the pressure at a point A. That is, work done is equal to force into displacement. Force is F1, displacement is that is a small displacement dx. So in this case, F1 can be written as in terms of pressure P1 into A. So here the area is, that is A1, right? So P1 into A1 into small displacement, that is a dx. So then area into displacement, it can be written as a volume. So that is a small change in its volume, that is P1 into del of V, because here we are considering a small time interval of del of t. So then in a small time interval of del of t, its volume changes through very small volume, that is del of V. So this is the work done by the pressure at point A. Similarly, the work done by the pressure, at point B, here is also same, that is the work done is equal to force into displacement, that is W2 is equal to force into displacement. So here force is F2, displacement, that is also same, in a small time interval it covers small displacement, that is dx. This is equal to F2, it is in the form of pressure, that is P2 into A2 into dx. So this work done, that is W2 is equal to P2 A2 into dx, that is change in its small volume. So this is the work done by the pressure at point B. So that is W2 is equal to P2 into del of V. So here this is our equation number 1 and this is our equation number 2. So the net work done, that is equal to W is equal to, or W suffix n is equal to W1 minus W2. The net work done, that is W suffix n is equal to W1 minus W2. Here W1 value is, that is P1 into del of V, and W2 value is, that is P2 into del of V, Here take del of V common, so the net work done, that is equal to P1 minus P2 into del of V. Okay, so in this case, this work done, it possesses the two types of energy. So first one is the kinetic energy of the liquid and the second one is the gravitational potential energy, because in this case this is a bend shaped tube. So the speed of the fluid, it is different at this position because the area of a cross section is different, and here the variation of a height is there. At A point its height is h1, at B point its height is h2, and this work done, it possesses the two types of energy. One is the kinetic energy and the one more is the potential energy. So next we are going to find out what is the change in kinetic energy and the change in potential energy. And we are going to find out the change in kinetic energy. So change in kinetic energy, that is equal to final kinetic energy minus initial kinetic energy. So already we know that to calculate the kinetic energy, the expression is, that is 1 by 2 m into final means, that is V2 square minus 1 by 2 m V1 square, right? So in this case take m and 1 by 2 as a constant term, 1 by 2 m bracket of V2 square minus V1 square, right? Okay, see here, in this case we are consider very small time interval, that is del of t, right? So in a del of t, that is a small time interval, in this time interval the mass of the system, that is also changes very small mass, that is del of m, and the volume is also, that is very small, that is del of V. So from the definition of a density, so density is equal to mass per unit volume, then mass is equal to density into volume. So in this case, the mass is also changed very small. So that is del of m is equal to density into change in its volume. So that is small change in its mass is equal to density into change in its volume. Just substitute this m value here. So here we are consider very small time interval, that's why the mass of the liquid is also changes very small, so that is del of m. So then change in kinetic energy, that is equal to 1 by 2 rho into del of v. So bracket of v2 square minus v1 square. See here we are consider very small time interval, that's why the mass of the liquid is also changed very small, that is del of m. So with the help of a definition of density, del of m is equal to rho into del of v. So substitute this value in this expression, then the change in its kinetic energy, that is equal to 1 by 2 rho into del of v bracket of v2 square minus v1 square. So this is the change in kinetic energy. Similarly, we are going to find out the change in potential energy, final potential energy minus initial potential energy. Potential energy expression is, that is mgh. The final means here mgh2 minus mgh1. So final potential energy, that is mgh2 minus mgh1. Okay, in this case the mass, here the mass is very small, that is del of m. So already we know that the del of m value is, that is rho into del of v. So take m common here, m value is, that is rho into del of v into g bracket of h2 minus h1 in bracket of h2 minus h1. So this is the change in potential energy. So according to the work energy theorem, that is net work done is equal to change in its energy, right? Change in its energy. Okay, see here the net work done. So what is the net work done value is here, that is P1 minus P2 into del of V, that is equal to change in its energy means, the sum of kinetic energy plus potential energy. The change in, see here the change in kinetic energy plus change in potential energy, right? Okay, see here in this case change in kinetic energy value is, that is 1 by 2 rho into del of v bracket of v2 square minus v1 square. Next plus potential energy value is rho del of v into g bracket of h2 minus h1. So in this case del of v take common, that is P1 minus P2 del of v, that is equal to del of v common in bracket of 1 by 2 rho bracket of v2 square minus v1 square plus rho g bracket of h2 minus h1. So in this case del of v both are get cancelled. The remaining is P1 minus P2 is equal to 1 by 2 rho v2 square minus v1 square plus rho g bracket of h2 minus h1. So next one we are going to multiply this term. So see here the equation becomes P1 minus P2, that is equal to, multiply this one, that is 1 by 2 rho v2 square minus 1 by 2 rho v1 square plus rho gh2 minus rho gh1. So after that rearrange the equation here. So then the equation becomes P1, so take this term this side, this is a negative sign, it becomes positive, P1 plus 1 by 2 rho v1 square, right? Next take this term this side plus rho gh1, that is equal to take this P2 term this side, this becomes P2 plus 1 by 2 rho v2 square plus rho gh2, H2. So in general, we can write this expression as P plus 1 by 2 rho V square plus rho GH, that is equal to constant. That is equal to constant. Okay, see here the pressure energy plus kinetic energy plus potential energy per unit volume is equal to constant. So this is the proof of this theorem. Bernoullis principle, what is the statement here? It is a sum of kinetic energy, potential energy, pressure energy per unit volume is always constant for an ideal fluid having the streamlined flow. So first one we are going to find out here, work done by the pressure at point A. After that, work done by the pressure at point B. So that is W2 is equal to force into displacement, F2 into displacement, that is dx. So here from the definition of a pressure, it can be written as the P2 into A2 into dx. So in this case, A2 into dx, it is the change in its volume. It can be replaced by the del of V. W2 is equal to P2 into del of V. So this is our equation number 2, and previous one is the equation number 1. So the net work done is equal to W1 minus W2. Here the W1 value is P1 del of E minus P2 del of E. So in this case, take del of E common, then it becomes P1 minus P2, right? So this work done, it possesses the two types of energy. One is the kinetic energy and one more is the gravitation potential energy. Okay, see here. Next one, we are going to find out the change in kinetic energy, that is equal to final kinetic energy minus initial kinetic energy, that is equal to final kinetic energy value is 1 by 2 m into V2 square minus 1 by 2 m into V1 square. So in this case, take 1 by 2 m as a constant term. The remaining is V2 square minus V1 square. So in this case, we are consider the time interval is very small, that is del of t. So in the del of t, the mass also change very small, that is del of m, that is equal to rho into del of E. So this is the mass value here. Substitute in this case, then the change in kinetic energy, that is equal to 1 by 2 rho into del of E bracket of V2 square minus V1 square. So this is the change in kinetic energy. Similarly, we are going to find out the change in potential energy, that is rho del of V G bracket of H2 minus H1, right? So the next one, according to the work energy theorem, the net work done, that is equal to change in its energy. So here there are two types of energy, then it is sum of kinetic energy plus sum of change in potential energy. Substitute all the values here. So after that, take del of V is a common term, both are get cancelled. Then the remaining expression is P1 minus P2 is equal to 1 by 2 rho into V2 square minus 1 by 2 into rho into V1 square plus rho GH2 minus rho GH1. So rearrange this equation, then equation becomes P1 plus 1 by 2 rho V1 square plus rho GH1, that is equal to P2 plus 1 by 2 rho V2 square plus rho GH2. So in general, we will write this expression as a P plus 1 by 2 rho V square plus rho GH, that is equal to constant. Okay, so here P indicates that the pressure energy, 1 by 2 rho V square indicates that the kinetic energy per unit volume, and rho GH indicates that potential energy per unit volume is equal to constant. So this is a proof of the Bernoullis theorem. What is the statement here? It is sum of pressure energy, kinetic energy, potential energy per unit volume is equal to constant. Okay, see here, in some cases they are given a horizontal pipe. So here they are given a horizontal pipe. Okay, so in this case, the height of the pipe at both sides is same. Here is also h, here is also h. So in that case, the Bernoullis equation, it will changes. Okay, see here, in general we will see here. So the h1 and h2 values are same. So in this case, h1 value is also h and h2 value is also h. In case of horizontal pipe, h1 is equal to h2 is equal to h. So substitute the h1 value here. This is h1 value is h and h2 value is also h. So in this case, both terms are get cancelled. In that case, the expression becomes that is P1 plus 1 by 2 rho V1 square, that is equal to P2 plus 1 by 2 rho V2 square. So in general, it can be written as P plus 1 by 2 rho V1 square or V square, that is equal to constant. It is for horizontal pipe. In case if the height at the two sides of the tube is same, in that case the expression becomes P plus 1 by 2 rho V square is equal to constant. The applications of a Bernoullis theorem, the first application is Ventimeter. So Ventimeter is a device which is used to measure the rate of flow of fluid through the pipe, right? So Ventimeter, it is a device it is used to measure the rate of flow of liquid through the pipe, so that is known as the Ventimeter. And this Ventimeter, it consists of two identical pipes. It consists of two identical pipes. So first pipe is that is A and the second pipe is that is B, right? And these two pipes are connecting with the help of a narrow pipe, with the help of a narrow pipe that is C, right? So this is our reference level or horizontal reference. So in this case, the height of the first tube from the horizontal surface is H1, the height of the second tube that is B, that is also height is same, so that is also H. So in this case we are consider the height of the first tube from the horizontal surface is H and the height of a second tube is also from the horizontal surface is H, and here we are connecting a narrow pipe. Okay, so this is the construction of a Ventimeter. So the Ventimeter, it consists of the two identical pipes A and B. With the help of a narrow pipe C, we are connecting these two pipes, and the height of the first tube and the second tube is same, that is H from the horizontal surface. So after that we are fixed the two vertical pipes. After that the liquid, it is flow in this direction, the liquid flowing through this pipe in this direction. So here we are consider the 2 point. So consider this is a first point A and this is a second point, right? So first point is A and the second point is B. So here we are going to apply the Bernoullis theorem at point A and at point B, right? So before that, already we know that the equation of continuity is that is AV is equal to constant, AV is equal to constant if area is inversely proportional to velocity or speed, right? So here area is inversely proportional to the speed. If the area is increases, the speed of the liquid is decreases. If the area of the tube is decreases, the speed of the liquid it is increases. Okay, see here, if in this case the liquid is flowing in this direction, at point A the speed of the liquid, so that is V1. At point A the speed of the liquid, that is V1. So the fluid is moving in this direction. When the fluid is reaching at this point, in this case the area of this tube is less comparing to the area of the first tube. So then its velocity changes at this point. The velocity of a fluid at this point is, that is V2. Here the V1 indicates that the speed of the liquid at point A and V2 indicates that the speed of a liquid at point B. So then according to the Bernoullis theorem, the pressure is inversely proportional to the speed of a liquid or the speed of a fluid, right? Here the speed of the liquid, it is more. The speed of the liquid is more. In that case the pressure at the point is less. The pressure at the point is less. If the speed of the liquid is less, at that point the pressure at the point is, that is more, right? Okay, see here, in this case at this point the speed of the liquid is less. Here it indicates that the pressure, right? See here, this is the height H1 and this is the height H2. So this gives the height, right? Okay, see here, the next one we are going to apply the Bernoullis theorem at point A and at point B, right? So already we know that the Bernoullis theorem for horizontal pipe, so that is P1 plus 1 by 2 rho V1 square, that is equal to P2 plus 1 by 2 rho V2 square, right? Okay, so here we are applying Bernoullis theorem at point A and at point B, right? So at point A, Bernoullis theorem, that is pressure at this point is P1 plus 1 by 2 rho V1 square, right? this is equal to pressure at the point B, that is P2 plus 1 by 2 rho into V2 square. 1 by 2 rho into V2 square. So then rearrange this equation, that is P1 minus P2, that is equal to 1 by 2 rho V2 square minus 1 by 2 rho V1 square. So in this case take 1 by 2 rho as a common term. This is 1 by 2 rho in bracket V2 square minus V1 square, right? So this is P1 minus P2, right? So from the equation of continuity, so that equation of continuity is, that is A1 V1 that is equal to A2 V2. So from this relation we want V2 value, that V2 is equal to A1 V1 divided by A2. A1 V1 divided by A2. So substitute this V2 value in this expression, right? Okay, see here. The next one here, P1 minus P2 is equal to 1 by 2 rho as it is, and here the V2 value is, what is the V2 value here? A1 V1 divided by A2. Substitute the V2 value here, that is A1 V1 divided by, that is A2 whole square, right? Minus V1 square, Okay, see here. This is as it is P1 minus P2, that is equal to 1 by 2 rho, and this becomes A1 square V1 square A2 square minus V1 square, right? So take V1 square as a common, so then P1 minus P2, that is equal to 1 by rho V1 square bracket of A1 square minus A2 square divided by A2 square. Okay, see here, in this case first we are taken V1 square is a common, then 1 by 2 rho V1 square, afterwards we are taken LCM here, then it becomes A1 square minus A2 square divided by A2 square. So in this case we want V1 square value, right? So before that one, P1 minus P2, it indicates that the pressure difference between any two points, that pressure difference is, that is rho GH. So already we know that the gauge pressure, the pressure difference between any 2 points, that is equal to rho GH. So here, so this is rho GH, that is equal to 1 by 2 rho V1 square bracket of A1 square minus A2 square divided by A2 square, right? So in this case rho get cancelled. So then V1 square, that is equal to 2GH, V1 square, that is equal to 2GH, take this term this side, that is A2 square divided by A1 square minus A2 square, right? So this is a V1 square value, that is 2GH bracket of A2 square divided by A1 square minus A2 square. So from this relation V1 is equal to, that is under root of 2GH into A2 square divided by A1 square minus A2 square. So then the speed of the liquid at point A, that is V1 is equal to A2 under root of 2GH divided by A1 square minus A2 square, right? So this is the speed of a liquid at point A. The speed of a liquid at point A. See here, the Ventimeter is a device that is used to measure the rate of flow of fluid through a pipe, right? Okay, see here, in this case we are consider the two identical pipes A and B having the same area of a cross section, and these two pipes are connecting with the help of a narrow pipe, that is C, right? So here the height of the two identical pipes from the horizontal surface is same. Then here we are considering the 2 point A point and B point. Here we are going to find out what is the speed of the liquid at point A and at point B, right? Okay, see here, already we know that the equation of continuity, that is AB is equal to constant, the area is inversely proportional to the velocity. Area is inversely proportional to the velocity. If the area is more, the velocity of the liquid at that point is less. If the area is small, then the velocity or the speed of a liquid at that point is more, right? So in this case, they compare it to this tube C, the area of a first tube is more. In this case, the speed of the liquid at this point is, that is V1. If the liquid is reaches at this point B, if the area is less, in that case the speed of the liquid is increases, because according to the equation of continuity, A is inversely proportional to V. Here the area is small. If the area is small, the speed of the liquid at this point is, that is changes, that is V2, right? Okay, here the speed of the liquid at point A is V1 and the speed of the liquid at the point is V2. So here we are going to apply the Bernoullis theorem at point A and at point B, right? Okay, already we know that the Bernoullis theorem for horizontal pipe, so its value is P1 plus 1 by 2 rho V1 square is equal to P2 plus 1 by 2 rho into V2 square. The apply Bernoullis theorem for point A and point B. At the point A, the pressure is P1 plus 1 by 2 rho into V1 square is equal to, at point B, the pressure, that is P2 plus 1 by 2 rho into V2 square. So rearrange this equation. P1 minus P2 is equal to 1 by 2 rho into V2 square minus 1 by 2 into rho into V1 square, right? So after that we have taken 1 by 2 rho as a common term. So that 1 by 2 rho bracket of V2 square minus V1 square. So already we know that the equation of continuity, that is A1 V1 is equal to A2 V2. So from this relation, V2 is equal to A1 V1 divided by A2. So substitute this V2 value in this relation, right? So then P1 minus P2 is equal to 1 by 2 rho bracket of A1 V1 by A2 whole square minus V1 square. So then P1 minus P2 is equal to 1 by 2 rho bracket of A1 square into V1 square divided by A2 square minus V1 square, right? So in this case, take V1 square as a common term. Here is also V1 is there, here is also V1 is there. Take V1 term as a common, after that take LCM. So then its expression becomes 1 by 2 rho into V1 square bracket of A1 square minus A2 square divided by A2 square. So here rho get cancelled. Here we want the expression V1 value, that is V1 square is equal to 2GH bracket of A2 square divided by A1 square minus A2 square. So then V1 is equal to, it is under root of 2GH A2 square divided by A1 square minus A2 square. So then V1 is equal to A2 square, right? The square root of A2 square, that is A2 under root of 2GH divided by A1 square minus A2 square. So this is the speed of a liquid at point A, speed of a liquid at point A, right? If you want to find out the speed of a liquid at point B, so in that case just we are substituting V1 value in this expression and simplify, we will get the V2 value.